Hey everyone, welcome back. Let's talk about another medium problem on Leetcode today, Jump Game, Leetcode 55. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an integer array nums and we are initially positioned at the array's first index. For example, we start with index 0 in both the examples, and each element in the array represents our maximum jump length at that position. And our goal is to determine if we can reach the last index in the array. If we can, then we will return true, otherwise we will return false. Then in example 1, index 0 has value equal to 2. So the maximum jump length from this position is equal to 2. Hence, we can take either one step or two steps. Now, if we take one step, we come to index 1, where value is equal to 3. So, we can take one step, two steps or three steps. And if we take three steps, we come to index 4, which is the last index. Hence, we will return true as our answer. Similarly, in example 2, we again started index 0, which has value equal to 3. So, we can take one step, two steps or three steps. So, if we take one step, we come to index 1 with value equal to 2. So, again, we can take one step or two steps, again reaching to index 3. And if we come to index 2, either from index 0 or index 1, we can just take one step because the value is equal to 1, again reaching to index 3 with value equal to 0, so we cannot move forward. So no matter how we jump, we will always arrive at index 3, which has value equal to 0, which makes it impossible to reach the last index. Hence, here we will return false. Now in terms of solution, the naive approach directly aligns with the example walkthrough. The idea is to simulate all possible paths to check whether the last index is reachable. If any path successfully leads to the destination, we immediately return true. For example, for this nums array, we start at index I equal to 0, where the value is equal to 3, which tells us the maximum number of positions we can jump forward. And for each possible jump, we recursively explore whether the next index can eventually reach at the last index. So when we start from index 0, we have three paths possible. Because the value is 3, we can either take one step and reach index 1, or we take two steps and reach index 2, or we take three steps and reach index 3. Now at index 1, the value is 2. So we can now take at most two steps. So either we can take one step and reach index 2, or two steps and reach index 3. And at index 2, we have value as 1. So we can take one step and reach index 3. But the value at index 3 is 0, which means no further jumps. So we have reached the dead end. So we need to backtrack. Similar is the case here as well. Now we again come to index 2 and note that this index is already explored, but we will re-explore it and we can jump to one index forward. So we go to index 3 and again we hit the dead end. And similarly we hit the dead end here as well. So since no path allows us to jump past the index 3, the last index 4 is unreachable. Hence we will return false as our answer. But if the value here was some non-zero value like 1, then we would have crossed to index 4 and returned true from this path. And if we can reach the last index from any path, then we will return true as our answer, as index 3 is no longer a dead end. This approach works, but the time complexity of this approach is O of n to the power of n, where n is the length of the input array, because the value at each index can spawn up to n recursive calls, resulting in O of n to the power of n recursive calls. And in terms of space complexity, it will be O of n, which is the depth of the recursion. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's initiate a depth first search starting from the first index, that is index 0. Now, the DFS function takes the current position and the array of jump lengths as input. First, we will check for the base case, that is, if the current position is greater than or equal to the last index of the array, it means we have reached the end or beyond, so we will return true. Otherwise, we will iterate through all possible next jumps starting from the current position and make a recursive call to move to that new position. And if any recursive call returns true, we will return true as our answer. Otherwise, if the loop finishes without finding a valid path, we will return false. Now, if we run this code, we will get time limit exceeded. So now the question is, can we do better? And the answer is yes. As we already saw, this recursive approach leads to redundant calculations. For example, here index 2 is calculated twice. So to optimize this, we can use caching, where we can use a data structure like hash map in Java or dictionary in Python to store and reuse results for previously calculated indices. And in the cache, we will be storing index as key and value as boolean, which is true if the last index is reachable from that index or false otherwise. So let's initialize the empty cache. Now we again start the recursion from index 0, where value is equal to 3. So we try jumping to indices 1, 2 or 3. Suppose we come to index 1, where value is 2, so we jump to indices 2 and 3. And at index 2 value is 1, so we jump to index 3, where the value is equal to 0. Hence, we cannot move forward. So we will be storing false as answer for index 3. And we backtrack and come to index 2. And from index 2, only path we took was to index 3, which returned false. So we will be storing false for 2 as well. And backtrack to index 1 and go to index 3. But the result for index 3 is already calculated, as we can see in the cache, and it is also false. So we hit the dead end for 1 as well. Hence, we will be storing false as result for index 1 as well. And now we come to index 0 and try going to index 2, for which the value is already calculated as false. Hence, we will return false from this path as well. And finally, from index 3 also, we will return false. Hence, in the end, our answer will be false for this nums array. And now the time complexity reduces to O of n square, because each index is now processed at most once due to caching. And for each index, we explore up to v possible jumps, where v is the value at nums I, which when comes to jump positions maximizes to n, leading to worst case time complexity of O of n square for n indices. And the space complexity will be O of n for storing the results in the cache and because of the recursion stack. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. This approach is very similar to recursive approach, just that here first we create a cache, which is hash map in Java or dictionary in Python, to store the results of previously computed indices, and then initiate the DFS. And inside the DFS method, apart from checking the base case, we will check if the result for this index is already stored in the cache. If it is, then we will return the cached result directly, avoiding redundant computations. Otherwise, we will compute the result and store it in the cache. So, when any valid path from the current index successfully reaches the last index, we will store true in the cache for the current index before returning the result. Otherwise, if no valid path is found, we will store false in the cache before returning the result. Even though this DP approach with caching is an improvement over the naive approach, running it on larger inputs will still result in time limit exceeded errors. Luckily, there is even better and simpler solution, which takes advantage of the greedy approach. Let's explore it. Now, to solve this problem, we have to start from the 0th index and move all the way to the last index, which is like our goalpost or target position. But now let's invert this problem. Instead of shifting our position towards the goal, let's shift the goalpost towards us. So we iterate through the array from right to left, and we update the goalpost whenever the previous index can reach the current goal. And in the end, if goalpost can reach us, we will return true, otherwise we will return false. So let's see this in action. Initially, goalpost is at the last index, which is index 4 here. Now we check if any previous index can reach this goal, starting with index 3, where the value is equal to 1. So we can have a jump of length 1 and reach current goalpost. Now since we can reach to current goalpost from index 3, we don't need to keep the goalpost at index 4. If we can reach index 3 from index 0, we can also reach index 4. So we update our goalpost to index 3. And here we were literally jumping from index 3 to index 4. But programmatically, we check whether the current index, that is 3, plus the value at that index, that is 1, is at least equal to the goal index. If it is, then the current index can reach the goal index. and we shift the goalpost backward to the current index. Moving forward, again we will check in the reverse direction, which is index 2, and here the value is equal to 1. So it can again make a jump of 1 and reach our current goalpost at index 3. Note that even though index 2 cannot directly reach the original goalpost at index 4, it can still reach index 3, which itself can reach index 4. Hence, we shift our goalpost to index 2. Now moving on to the next index in the reverse order, that is index 1, the value is 2. So it can make 2 jumps and reach index 3, or it can make 1 jump and reach current goalpost. But why jump 2 steps when jumping 1 step is enough to reach the current goal? So it will make 1 jump and we move the goalpost forward. And finally we come to index 0 where the value is equal to 3. So it can make 3 jumps, but all it needs is 1 jump and reach the goalpost at index 1. So we move the goalpost to index 0 and now we are at the end of the iteration. And since the goalpost has successfully shifted to the 0th index, this means the last index is reachable. Hence, we will return true in this case. Now let's look at a counter example where the last index is not reachable. Say we have 0 here instead of 1. So again, our goalpost is at index 4 and we start from right to left, starting with index 3 to check if we can reach the current goal. And here the value is equal to 0, meaning there are no jumps possible to reach the current goalpost at index 4. So we will check if the next index can reach the goalpost where the value is equal to 1. And from there, we can jump to index 3. But if we jump there, we will get stuck there. So again, we can't reach index 4. And hence, we move to the next index and see if we can reach the goalpost from there. And here the value is 2. So maximum we can jump to is index 3. But we can't reach index 4 from there. Hence the goal remains 4. And we try out the next index with value equal to 3. And the maximum we can jump from this one is 3. So again, we can jump till index 3, which will result in dead end. Now we have come to the starting index, but the goalpost stays stuck at index 4 and never shifts backward to index 0. This means the last index is unreachable, hence we will return false as our answer. Now the time complexity reduces to O of n because each index in the array is processed only once, and the space complexity is O of 1 as we are using few variables here and there. Here is a quick code walkthrough of the algorithm we just talked about with Java code on left and Python on right. We start by setting the goalpost to the last index. This represents the minimum index we need to reach to be able to jump to the last index. Now we will iterate from right to left through the indices of the array, starting from second to last index. And for each index I, we check if it is possible to reach the current goal from this index by considering the jump length, which is value at that index. If the current index I plus value at that index, that is nums I, is greater than or equal to the goal, it means we can reach the current goal. Hence we update the goalpost to the current index, as now we only need to be able to reach this new goal from the beginning. And after the loop finishes, we check if the goal has moved all the way back to the starting position. If it has, that means the last index is reachable from the starting position and hence we will return true. Otherwise, we will return false. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.